So now we're going to see how to deal with a different situation in combining functions. We're going to see how to deal with composite functions. So what happens when functions are within other functions. And this is going to be the chain rule. So we know how to find something like the derivative of 2x plus 3 because we have rules that say we could just do the derivative of 2x and get 2 and take the derivative of 3 and get 0 and we'd be done. But how do we deal with something that is a little more complicated and say the derivative of 2x plus 3 to the fourth? Specifically, how do we do it without multiplying out 2x plus 3 to the fourth, which we would like a way not to have to do that? Well, that's going to involve the chain rule. And the basic idea is that we have the function 2x plus 3 inside the function x to the fourth in a composite situation. And we're going to use that idea via the chain rule. So let me explain the chain rule, or let me go through the wording of the chain rule. We'll look at an example that explicitly goes through the chain rule, and then we'll see a kind of a shorter, faster way of doing it. Okay, so the chain rule says if y, which is y of u, so we're just saying that y is a function of u, is a differentiable function of u, and u equals u of x is a differential function of x, then y, which is now considered as y of u of x, is a differentiable function of x. Let's pause for a moment. So we still have the y function, but what we've done is we've taken the u function and put it in for u there, making now y ultimately a function of x and getting rid of really the u that we were going through. Okay, so the differentiability holds, and if we want the derivative of y with respect to x, we can get that by doing the derivative of y with respect to u times the derivative of u with respect to x. And this is the little chain that's established here in order to go through the different variables. Okay, so let's see how this would work in our example and see if it makes sense. So from our example, we were looking at the function 2x plus 3 to the fourth. So let's structure that as described in the chain rule. The y of u here would be u to the fourth. That's this outer function that is taking something, in this case 2x plus 3 to the fourth, but we're going to let that something be u to the fourth. So y of u is u to the fourth, and u of x is that something inside, that's the 2x plus 3. And before we get to the derivatives, then you see that if u of x is 2x plus 3, then what we're saying is that we have u to the fourth, but what we do is we get rid of u, and instead we do 2x plus 3 to the fourth, and that's how we're building the function. All right, so let's go to the derivatives now. If y of u is u to the fourth, then the derivative of y with respect to u is just 4u cubed. And then if u of x is 2x plus 3, then du dx is just 2. That's our usual derivative. Okay, so then what does that tell us? Again, we can say that dy... Oh, this should actually be, hold on. This should be dy dx. Let me fix that, dy dx, because that's ultimately what we want, is we want y in terms of x, and to get rid of the middle u. So dy dx is dy du times du dx. Although it's not really how it works, you can kind of think about this as, you see the du's essentially cancel out, and what I'm left with is dy dx. But that's more of a conceptual thing. It's not really how it works. Okay, so from above we have 4u cubed as dy du, and then dy dx is 2, so we get 8u cubed. Now the thing is, if we were getting rid of u, so just getting to y and x, I don't think we want u in our final answer. But we remember we know u of x is 2x plus 3. So in the end, this becomes 8 times 2x plus 3 cubed when I take u and replace it by the 2x plus 3. Okay, so that's how it works in theory. Ordinarily, we don't have to go through all of that dependence on another variable in there. So it's often easier to think of it in this framework. Let's call the composite function f of g of x. Okay, and we're not always going to have to really explicitly list what is f of x, what is g of x. We'll be able to do it on the fly. Okay, so the derivative of f of g of x is the derivative of f at g of x times g prime of x. Okay, then let's see how this works here in this situation. So basically, if I want to redo that example, I'm looking at the derivative of 2x plus 3 to the fourth. And what I really have to do is I have to identify what is the outer function and what is the inner function. All right, from the most outside look at this, it's basically what I'll say is something to the fourth, okay? Where that something, just clean up that 4, that something inside we'll deal with in a minute. So that something is really the g of x that's inside. So I have something to the fourth. Now we've seen that if you have something to the fourth, then that would be 4 times the something cubed, with the power rule. Okay, so now the only difference here is that something I just hold on to and I put inside 2x plus 3 cubed. Okay, that's this part right here that I just did. That's the derivative of f still at g of x, derivative of f at this something. But then what I still need is I need this derivative of g. So I need to multiply by the derivative of 2x plus 3. So that's this part here. So I end up with 4 times 2x plus 3 cubed, and the derivative of 2x plus 3 is just 2. And as you see, if I multiply the 2 and the 4, 8 2x plus 3 cubed. Okay, and we get the same answer. That's more of the approach that we'll take. We're going to work from the outside in on our derivative taking. And you'll see we can do it with multiple levels, not just 2 levels here. So the idea is, again, identify the makeup of the function. I have something to the fourth. So then basically I do a power rule and I say the 4 comes out in front and then decrease the 4 to a 3. And that's how I get this part here. But then I have to go inside and take care of the something that I was holding on to. And that's where I take the derivative of that. And that's how I get the 2 factor as the chain rule factor there. And then I end up with my answer after I simplify.